hemodynamic management.
Thank you very much. I'm reminded by Luciano Gattinoni, who said to me, I'm not worried about artificial intelligence, I'm worried about a lack of natural intelligence. And the point is, thank you, that there's no substitute at this present time for an intelligent physician observing or clinician observing the patient at the bedside. Everything else we do is associated with that. These are my conflicts of interest, and they're directly related to what I'm going to talk about, because everything I've ever done is related to hemodynamic monitoring. But importantly, I'm the inventor of 2 U.S. patents. The first is the dynamic arterial elastance, which you saw in the last lecture is being used for the algorithm. But the second is that we have an approved patent on looking at complexity modeling to identify critical illness. And that was a patent that I submitted primarily so that it didn't have to be defended, so that no company could make it theirs, so that everyone can use artificial intelligence to manage patients. So that's just out there, okay? So don't be surprised by the unexpected. Prepare for it, but can it be predicted? When we're talking about using artificial intelligence for hemodynamic monitoring, what we're doing is we're not using new tools, we're just looking over time. And if you look at the exact same data over time, evolving patterns become obvious with no change. This is a picture of the night sky. I haven't changed the night sky. I haven't changed the way in which you look at it. I've just looked at it over time. And as you see from this, there is an evolving pattern that demonstrates exactly where the North Star is, for example. So let me give you an example of evolving patterns and how we can use machine learning for it, and then the principles behind it. Nobody talked to you about the principal components and the featurization, but what we do in machine learning is we take a waveform and we look at all the different features that are from it. And then using machine learning, because the computer can do it, we look at multiple 100,000 correlations. You could have done every single one of those correlations yourself once, but it would take a lifetime to do the 100,000. But machine learning can do it in a couple hours. So that's the reason why we use these models, is because they're doing statistical analysis and looking at things, and they tell us what's useful. It is then up to us as human beings, as doctors, to say, is this rational, what they say? This is an example of a human being in our lower body negative pressure chamber, in which all we have done is increase the degree of negative pressure in the box below their abdomen, which is the equivalent of hemorrhage. Every 10 millimeters of mercury drop is equal to about 400 mLs of blood loss. And as you can see, as you progressively increase the box to more and more negative pressure, the stroke volume progressively falls down, but the blood pressure remains constant up until the end. What I want to show you is the non-invasive measurement of pulse oximetry. And if not looking at the oxygen saturation at all, I really don't care about oxygen saturation because it's almost never an important issue in my patient. But if you look at the pleth signal itself here shown, and I were to show you a little bit closer, you can see how as you get lower and lower in terms of your stroke volume with the same mean arterial pressure, the change of the pleth occurs with loss of reflected waves. Interestingly, we do the exact same data collection, but not during lower body negative pressure, but during air transport of critically ill people from a scene. And this is an example of one patient who was emergently intubated on a helicopter, and you can see the exact same mirror image of that featurization in them as well. So this is the sort of featurization that we're talking about when in my lecture I'm asked, what is the hemodynamic monitoring that we should be doing? It isn't that we're using a pulse oximeter, it's what are we doing with the pulse oximeter's information, okay? That's not the same thing. So I'm not gonna go through all of these, there's not enough time in my 10 minutes, but we can early identify, I will show the triage, what can be done, and this is being done right now. I can tell you who is not going to be sick when they're admitted to the hospital within 15 minutes of them being arrived, and I can tell you for the next 2 days they will never crash. I can tell you that with great accuracy in patients admitted with trauma and post-op surgery. I'll show you that in a second. We can do latent group analysis, which is simply saying that we know that there are different subgroups of people. For example, ARDS, we've always talked about primary and secondary ARDS, right? So it's not surprising that the two look different. But within each one of those, there are subgroups as well. And we can use it for prediction. We can have smart alarms. One of the things we focused on from the very beginning was to eliminate artifacts in real time so that when the alarm goes beep, it's real. It's because we wanted to eliminate alarm fatigue. And that's what I spent the first 5 years of our work on this working on from a technical perspective. And then finally, we have intelligent clinical decision systems, which is I'm working on now. In an open loop system, patients, the physicians, clinicians can reject it, but there is zero rejection if it's a closed loop system. So you have to make sure they're very accurate. So I wanted to talk to you about predictive analytics. And it was said earlier, you can't predict the future. But you can identify subtle subliminal things that are present in the data right now that are signatures of what's going to happen in the future. And that's going to be a lot due to the nature of the patient, et cetera. But you can follow these things nicely if you have adequate data collection and you're looking at it. To be able to identify exactly how somebody is right now, we refer to as nowcasting. But to predict who will crash based on data, that's forecasting. So Gilles Clermont and Fu Mandeli, when she was with us before going to Johns Hopkins, looked at the respiratory heart rate variability metrics, multiple features. And we knew that some patients were going to crash and others weren't. So in the training set, we identified what were those features that were present in the heart rate variability that were seen in people that would crash and wouldn't crash. And then we took about 200 patients that were part of our training set, and we ran it on them as well. And we walked backward from a code being called for cardiorespiratory insufficiency backwards. And this is over a period of 10 days. And this is an important point. We were able to clearly separate out those people who would crash from those people who wouldn't crash 48 hours beforehand. And this is universally seen across all data analysis. Very rarely do patients who are crashing of their own volition, not surgically, do it over a minute or two. It takes hours, and you could see it if it's there. And what we saw was they could separate them. Patients who had a high level of heart rate variability based on our features were healthy. The lack of heart rate variability was bad. We talk about stability as being good, but I assure you there's nothing more stable than death. Okay. What we have is we have a baseline level of stress, and let's assume somebody's getting sick, and that's whatever the metrics are, and at the present time, we don't identify 80% of the patient when they reach the level that we should see them. We've already heard that. This is our current performance, but with appropriate nowcasting, we should be able to say that when the machine goes beep, see the patient and they're sick. And that would, of course, allow us to treat earlier. And if we looked at subliminal things that would not be considered abnormal, we could move that time to an earlier point, and therefore I need less effort to treat the patient. It's now been 11 years since we performed this first trial. Using Oxford Biosignals analysis of our own data, we created an artificial neural net with just 3 nodes to look at pulse oximeter, O2 sat, heart rate and respiratory rate and intermittent blood pressure to determine about 300 patients in our step-down unit if they were healthy or sick over time, and we had it in a display. The sicker they were, the vital sign index got bigger or smaller as a balloon, and the balloon itself was a pie, and whether it was respiratory rate, O2 sat, blood pressure, or heart rate, determining the pie getting higher would be there so they could kind of see it. And so before we started it, we did a sampling of our patients in the step-down unit to say how many times was the medical emergency team activation occurred, and how many of the times was it minor, it was something you could have fixed, and how many times was it major and I would have called a code. And then after we'd done this for 6 weeks, we took those data and created a model and showed to the nurses at the bedside in real time that same number. And we said, no more Mr. Nice Guy. If this machine goes beep because the number goes above 3, you absolutely positively have to see the patient. If you can't fix them, call a code. And that's all we told them. And by the way, we didn't tell the doctors we were doing this. And what we found was that we didn't decrease the degree of minimal instability, but we profoundly decreased the number of patients who went on to a full code. And the nurses told us that the ICU became quieter, all the other alarms stopped working because the patients were stable and they had more time to take care of their patients. We decreased the alarms by 50% of all the other vital sign alerts because we didn't take away their alerts. And furthermore, what we really did was it was able to treat the patients earlier, but when they were really sick, it took the same amount of time to take care of them. Okay. Looking at that data, we were able to ask the question, when they first came into the step-down unit, after they'd been there for 15 minutes, we just took 15 minutes of data, and we said, in a training group, we knew they'd eventually crash. In another group, we knew they wouldn't. And we're talking heart rate, respiratory rate, O2 sat, and one blood pressure measurement. And based on this, we were able to create a signature of what we consider to be stability and instability. And if you looked at them at the 4 hours beforehand, and then we could identify accurately who would never crash. And of course, when they finally did crash, it was higher, but they were already unstable. But we were able to do this in 80% of the patients. We weren't trying to identify stability, but it turned out we could identify stability very well. But it was hard to determine when they would crash because they were already at a higher level. So if you looked at that exact same data and said, let's make it their normalized data, it doesn't matter what it is, we're going to say it's normal for them. And then you look at what happens when they go on their normalized data, not changing the data one bit. Now we had the ability to identify forecasting. And we could identify it in more than an hour and a half beforehand. And furthermore, if you look at latent group analysis, there were 5 separate groups of instability that occurred. The black line is the stable ones, and that is disease. And in fact, the groups were different in terms of their demographics and how long they needed to be at baseline risk and different times in the hospital. So in disease, you follow certain pathways. Which pathway you're on at this moment, I don't know. But within 15 minutes of seeing you, I can tell you which pathway you're on. And these latent group analysis can be done for other groups. Sujan Park, who will be talking after me, graciously allowed me to be a co-author on her paper, in which we looked at the endotypes of COVID-19 patients in the ICU, and we were able to separate them into 4 separate groups, and they were completely different in terms of their demographics. So now let's go on to my topic, which is hemodynamic monitoring. Okay. The real question that I like to talk about is hemodynamic monitoring parsimony. Now, I'm a big believer in the rule that the one who dies with the most toys wins. But that is not the way I should manage my patient. I should use the minimal data set necessary to identify what it is. And so we define that as what is the minimal number of primary variables and their featurizations that are necessary to identify disease, and what is our sampling frequency? Is it once an hour, once a year, beat to beat, or waveform? When you see your doctor as a healthcare follow-up, it's usually once a year. That's not going to be good in the ICU. But is 5 minutes good enough? Do you need beat to beat? And how long do I have to observe before I know what's going on? And I'll tell you right now, except for looking at it at a single snapshot, which tells you if you're alive or dead, single observations are close to meaningless. So we want to determine the performance. But how do you determine the performance of your ability to say somebody is sick or bad? And it's really not the area under a receiver operator characteristic curve. What you really care about is how many times does the machine go beep when there's nothing wrong? That's a false positive. Or how many times does it say you're fine and you fall over dead? That's a false negative. Those are the 2 things that count, and those are the 2 things that keep all of us up at night. So in a series of studies, we looked at all the hemodynamic monitoring we could do in an animal model of hemorrhagic shock. And they had a baseline value, and the reference is below. And then we started to bleed them at about 20 mLs a minute, 5 mLs a minute, or nothing. And at 5 mLs per minute, it takes like a half an hour before any change has occurred, anything you can measure. And then we looked at the features that describe the anomaly of those animals using a leave one out cross-validation random forest attack, so that anyone's in the machine learning, you know what I'm talking about. Never mind, we used fancy computer analysis to look at the data. And what we found was we could accurately follow the cloud of bleeding when there was no measurable change. That's for all the data. Do I need an arterial catheter? Do I need a central venous catheter? Or can I use non-invasive metrics? That was the next question we asked. So using that exact same data, we looked at the activity monitoring characteristic curve. And you have to understand how this works. What you look at is the number of false positives, how many times the machine goes beep when nothing happened, and how fine after the event started did you get it. Now what you'd like to have, as soon as the event happens, the machine goes off and there are no false positives. What do the machines in your hospital do, the monitors? They have they're sensitive all the time. If you want to not miss a single time, have the monitor going off continuously. Because once there's an instability, the monitor will still be positive. But that's meaningless. And that causes alarm fatigue, but that's what we have today. So what you want is you want to have a low alarm, and this is the log scale. This is 1 in 10 times it's wrong, 1 in 100 times, 1 in 1,000 times. And over here you can see the various measurements. This is non-invasive measurements, the use of a central venous catheter, arterial catheter, the arterial catheter with cardiac output, PA catheter with arterial pressure. And you can see that if you have just looking at it every 5 minutes, you won't be able to identify bleeding until you're well into about 10 minutes into the bleeding with all of them. It's pretty poor. And this is the featurization of it. So if you just take 8 minutes as an example so I can give it to you as a reference, this is what you see. If I now instead, with the exact same data, don't look at it every 2 minutes, but look at the beat-to-beat variables, which allow me to cause greater degrees of featurization of it. You can see all of a sudden that at 8 minutes, I can be extremely accurate at predicting instability with 1 in 100 false negatives. That's clinically relevant. 99% of the time when I hear the beep, it's real. But that would only be with either the PA catheter or the PA catheter plus the art line. If I now look not at beat to beat, but look at the waveforms. And with the waveforms, what I look at is how they go. You can see now that almost all devices give me data equally. So across the line, if you were to see it, now with waveform data, a central venous catheter is useful. An art line is useful. So the question is, which monitor device you have? My answer to you is, how often are you monitoring it? Finally, if I know that the patient was stable before and they're now being unstable, this is the predictive value of simple metrics. That's every 5 minutes, beat to beat and waveform. And as you can see at 8 minutes, it's here. If I know what their normal baseline was, everything works better. Who would that be? Well, that would be a pre-op surgical patient, because theoretically they were stable before and then post-operatively. And when we looked at that exact same data, for those waveforms, I already showed you this is the waveform data without having a baseline. But if you had a baseline, everything works well. Central venous catheter still works. It's not the CVP I'm looking at, it's the features of the CVP. So we can actually develop this into a smart system, which we call IQ, which allows for the data to alert people ahead of time. And to get on to our chair's question, it's not a yes or no, it's a threshold thing. It's getting worse and worse, or they're getting better and better. And so in the future, we're going to monitor the monitors, but treat the patients. And we're going to look at artifact detection so that on the fly, as we're looking at it, the models we have will be more robust. And we'll use fuse parameters to assess them. And the thing we do at the University of Pittsburgh is we have a predicting instability time and treatment. It took us forever to figure out a thing that would call us to call it PIT. the PIT index, and there are the values down below, and there's a predicted thing, and there's our pie showing you which things are causing it. And if you treat the patient, this is telling you the probability of the event and the time. If you treat them, the probability of the event falls, and you run away from the time in which it would occur. And with that, I thank you for your attention.